Good afternoon, everyone. Thanks for joining us again for another installment of our seminar series. We're going through Yang-Mills theory. So we've had a look at the basics of gauge theory, and we've had a look at a particular example of these equations, namely Maxwell's equations. So now we're hoping to take a bit of a deeper dive into the structure of the Yang-Mills equations. So to that end, I'm pleased to invite Vishnu to talk to us about some of the good and bad things that happen with the Yang-Mills equations. So thank you, Vishnu.
Thanks, Tim. So, yeah, maybe I'll start by doing some kind of revision. But so I'm mainly going off where Max ended up, where he talked a bit about defining principal bundles, connections on principal bundles, and then he talked about the Yang-Mills functional. And then he looked at the Euler-Lagrange equation of that functional and wrote down the Yang-Mills equation. So I'm going to kind of follow using his notation, but maybe I want to point out that all the stuff we've done with Yang-Mills so far has been on principal bundles, but equivalently, you can formulate all this stuff on vector bundles. And actually, I'm going to do principal bundles. I'm going to continue on that because there are situations in which you want to do that. But a lot of the notation and maybe kind of wrapping your head around this kind of difficult stuff that involves principal bundles goes away when you work with vector bundles. So it's a good idea to actually look at all this on vector bundles as well. For example, you can write down a very explicit formula for the exterior covariant derivative on vector bundles. On principal bundles, you can do that as well, but you have to restrict if you want to write down a formula, you have to restrict the types of forms that you are acting on. Anyway, so let's start with a review. So recall that a connection on a principal bundle I'll call that P over some base space M is given by a Lie algebra. So this is a principal G bundle for some compact Lie group G, and this G is the Lie algebra, G valued one form. So I'll denote that by A in the space of one forms on P with values in G, which satisfies these two properties, which might not look familiar because it's not exactly the way that it was stated before, but it's a lot more useful to work with this thing called the connection form than it is to work with horizontal subspaces. So it satisfies these two properties, which is that if I take the adjoint action and under right translation, pull back my right translation of A, and that's the same as A. And then if I so I have this principal bundle, on a base manifold M, and then I have its fibers, which kind of look like Lie group G. Then if I look at the vector fields, given a element of the Lie algebra on a Lie group, that generates a vector field, a left invariant vector field. Then similarly, I can take on a principal bundle, given an element of the Lie algebra, I can generate a vector field that is sort of parallel to the fibers, right? And so given some element of the Lie algebra, then this, I think they're called fundamental vector fields, possibly. Then A of the fundamental vector field associated to X is just equal to psi. This gives me back that vector psi, right? Because that's in the Lie algebra. Okay, so actually, so Max did talk about the connection forms. That's the kind of way you study. That's the most easy way to study connections. But the way that connections were kind of defined were using these horizontal subspaces. And so the horizontal subspaces, H at a point P, you can write it as the kernel of this form A. Okay, and that's the relationship between those two things. So I'll use the space of connect. I'll use this notation AP to be the space of connections on P. Okay. So maybe for later, for when we do more analysis, we will end up relaxing this space of connections to be space of connections that are maybe differentiable, that are in a Sobolev space or something. So maybe we'd use AKP or something. Okay, so associated to a connection is the curvature 2 form, right? So we have the curvature 2 form. So that's FA, which is also a Lie algebra value 2 form. And there's a nice formula that tells you what it is. It's FA so it's the exterior covariant derivative of A, which is dA plus A comma A. Okay. So yeah, so this is I think it's called the Cartan structure equation or something. And this tells you how to compute the curvature from the connection form. Then the Yang-Mills functional is given by this integral here. So associated to this to a connection form, we have integral over m of the norm of FA squared over m. Okay. So this norm here, maybe I'll just say something about the norm. So if I have this norm FA squared, that's equal to, well, sometimes we write it like this, minus trace of of FA ij FA ij. So this the FA lies in the space of 2 forms in P with values in the Lie algebra. So this norm on the space of 2 forms, Lie algebra value 2 forms, has a component which comes from, okay, I should say that M is a Riemannian manifold, right? G, Mg. So there's a component that comes from the Riemannian metric, and there is a part that comes from the Lie algebra. So I think there's some technicalities here, but on certain Lie algebras or corresponding to Lie groups, there is a distinguished inner product given by the killing form. The killing form is what this trace here is. And it's negative definite, so if you put a minus in front of it, it becomes positive definite. But one important property that this killing form may be read as B, X, comma Y for vectors in the Lie algebra. It has an important property that if I take some other Lie algebra element of the Lie algebra Z, well, my pen is being a bit weird. ZX, ZY, then this is the same. Oh, okay, well, they're equal. Yeah, I've written it there. Right, so this B is ad invariant. Now I think in order to define this inner product here, you need this G to be compact, right? I think this killing form, I think existence of it is somehow equivalent to the algebra being semi-simple or something. But anyway, we can assume all that's true, and that we
I
have
think
this.
you get existence if it's compact, uniqueness if
Okay.
it's semi-simple or something like
Okay.
that.
Well, then, if it's compact, that's good enough. Then we just choose one of them. I think it should be good enough. Maybe, I'm not sure. But by the way, on vector bundles, like, you don't have any of this. You don't have to worry about any of this. Okay, so this property here, this ad invariance, we can call it ad invariance. is quite important for what I'll talk about soon, because as it turns out, when you do gauge transformations, that's equivalent to doing that's equivalent to the action of this add here. Okay, and then so Max then showed that the Euler-Lagrange equation for this functional is given by the adjoint of the exterior covariant derivative acting on FA. Okay, so this adjoint is defined by, so if I have integral of m dA alpha comma beta.
Oh, sorry, Vishnu, back to the Lie group thing. I can't remember if this is exactly what you said. My statement, I'm not sure if I said it properly, but the true statement is that compact Lie groups admit bi-invariant metrics.
Okay, I see. So you
For
need something else. Yep.
for semi-simple Lie group, such a metric I think is unique and has to be the killing form. So for
Okay.
semi-simple compacts, the killing form is fine. Compact is still fine. You can find a bi-invariant metric, but it's not going to be the killing, not necessarily going to be the killing form.
So bi-invariant, does that give me this property here?
Yes, I think so.
Okay, that's good enough then, I think. I don't know if it comes up anywhere else, but yeah, that's good enough. Anyway, yeah, so I'm on a manifold without boundary then, so this is the definition of the adjoint. Okay, so now what I want to compute is I want to write down this equation in terms of A in a way where I can try and understand if this is elliptic or not. So to do that, I'm going to repeat some of the calculation that Max did before, but this time I'm going to expand it a bit more. So let's take two connection forms. And we'll compute this thing like before. And that gives me integral of m of fa comma. So this time we get db plus a comma b. Okay, so then, so we can write that down as fa db plus fa a bracket b. So then, so here we can move this d to the other side and replace it with the codifferential. And here we can use a property of this trace that allows me to move this bracket to the F and the A. So I get this. Okay, so in the end we get, I'll just write out one more line to get D star F A comma, oops, plus F A comma A in a product with B. So then we get that this this exterior, the adjoint of the exterior covariant derivative applied to FA is equal to D star FA.
Sorry, Vishnu,
Yep.
question. Is this at invariance somehow like you switch the brackets from right to left? Does it follow from the at invariance you wrote before?
I don't know. May possibly.
Because
Maybe.
isn't killing form invariant with respect to like the algebra action? That is exactly the thing you've done in the computation.
You mean this one here?
I don't see where you're pointing.
Oh, okay, it's this one here.
Yeah.
I'm not sure. I didn't do these calculations in detail. And I actually think that what I've done here might not exactly be correct because
Okay.
well, it's almost correct. I think it actually should be the other. Possibly there it looks slightly different than this. It's some kind of bracket of FA and A, but it might be the other way around, or it might be negative or something.
Okay.
I couldn't exactly figure out because I'm not I don't it's not just like a Lie bracket where you can swap these two things here and you get put a negative sign. I don't think that's correct because when you apply this this form to, like, let's say XYZ, it applies XY to FA and then Z to A. So if you swap it, you're not getting, it doesn't appear to be anything related to the original form. So so yeah, this something like this is true, I know, but I think if you look online, it actually looks more, it says this usually AFA, something like that. So I'm not sure. Maybe I can look it up, but for the purposes of what I'm about to do, I really only care about the highest order term because I'm looking to see if
Sure.
yeah, but maybe so, but yeah, I'm not exactly sure. Some of these calculations are a bit not really something I know that well.
There was a question in the chat, just
Oh, yep.
so you know. I think
This one here?
yeah,
Sure.
it says, can you explain the first line again? I don't know if it's this a calculation or not.
Yeah,
Yeah,
sure.
sorry. Yeah, the first line of this differential.
Sure. Let's just let me just write it down. So we have so this is going to be, so I'm looking at this quantity, integral of over m of fa plus tb. So let's put an arrow here. Fa plus tb in a product with fa plus tb without the and so that's so I'm using the Cartan structure equation, so that gives me d a plus tb plus a plus tb in a product with, I'll just write fa plus tb. Right, same thing. D mu. So then what you do is we're differentiating with respect to time. So you expand these two things and then you just take the terms that have order t. So that will be the dB. So I'll just have a 0th order term plus t dB plus, and then this part, if you expand it, you just get the, okay, so you do need to do some things here, but I think if you look at Max's notes from last time, he does this calculation in detail, but then you get just the plus t a comma b. Right, and so when you differentiate it, this term, this t goes away, and you get db plus a bracket b, and then this term, the t you just set to 0, and so you just get fa. Does that make sense?
Yeah, but you'll get it twice, the bracket a comma b or not.
I think there is a reason that you don't get it twice. Because
Is b comma a same as a comma b here, or right?
no. This is so how is this thing defined? So A comma B. So this is a Lie algebra valued form. So A and B are one forms with values in the Lie algebra. No, this is a Lie algebra valued two form. So if I apply this to two vectors x comma y, then this is the bracket, the Lie bracket of A, x, B, y. Okay,
Yes.
so
Yes.
yeah, so this is not, so if you swap A and B, BA, it's something else. It's not quite,
Yeah. Yeah.
yeah, it's not negative AB.
Okay.
So yeah,
Yeah. Anyway, you can continue.
yeah, I'm not actually sure. So it's a bit confusing to me. But either way, still, I just care about the highest order term and for this calculation. So where was I? Okay, so yeah, so I'm writing this thing down. This thing that may not be correct, slightly correct, but at least the highest order term I know is correct. FA is D star FA plus FA comma B. And this is the Yang-Mills equation. And so now I'll just plug in what my value for FA, it's D star DA plus A comma A plus FA comma B. So basically, I'll just ignore all the lower order terms and I'll just get D star D A plus lower order terms. Because you know this is the only thing that the ellipticity of the equation only depends on this term here, right? I'll just write it. I'll just expand it one more time. I mean, well, I'll just write it as the Hodge Laplacian, which is okay. So that's D star A plus D star D A minus D star A plus lower order terms. And this thing here is the Hodge Laplacian applied to A minus D star A. Okay. So I'll just call this, let me write it like this. And then we can call this thing the operator L. So we can just see, by the way, that this is a semi-linear equation because it's linear in the highest order term. And in the lowest order terms, it's not linear. Lower order terms, okay? So we want to calculate the symbol of this operator and see what it is. But okay, you can kind of observe that it doesn't quite look elliptic. You have the Laplacian, but then you have this term, which is minus the derivative of a divergence, right? The codifferential is the form version of divergence, especially for one forms, it basically is a divergence. So, yeah. So let's calculate the symbol of this operator. So I looked at this book, which I found this nice book called Geometry of Manifolds. By, I didn't write down the name. Well, okay, I can't remember, but I'll definitely say it next talk I give. But in chapter 10, it explains exactly, it gives a whole chapter with lots of detailed explanation on how to calculate symbols of any differential operator that might look very complicated. So I would recommend reading that if you want to calculate symbols of things like the exterior derivative of the codifferential or any kind of combination of those things.
Was this Bishop and Christendon?
No, it's not.
Not that one. Just
Yeah.
looking up books with that name.
Okay, so, well, the symbol of L, so applied to some form and then acting on some vector omega. No, a form omega, because A is a form, so it acts on forms. So that's going to be the symbol of the Hodge Laplacian minus the symbol of d star psi. And so this one, hopefully everyone's happy that it's minus xi squared omega. Laplacian, it's always xi squared. By the way, so if we want it to be elliptic, it means that this thing, this operator without the omega, that operator which acts on omega needs to be an isomorphism. So now a nice lemma in that book that I didn't give you the title, the full name of, is that if you compose operators, then the symbols also compose.
I can see lectures on the geometry of manifolds by Nicolaescu, and there's a
Oh yeah,
chapter 10 on.
Yeah, lectures on geometry of manifolds. That's it. That's it. Yeah, and so in that book, he shows and explains why a symbol of the exterior derivative is wedge product. So if I have this thing applied to omega, then that's equal to xi wedge omega. And if I take the symbol of the codifferential, very neatly, it is interior product with the metric dual to xi applied to omega. Yep, that's it. That's the notes. Kind of what you expect. Well, I mean, not what I expect, but you expect at least that it has to have this thing should involve the dual of xi, because this codifferential does depend on the metric. So now composing these two, we get that this thing here is omega contracted with the metric dual to xi multiplied by xi. Oh, yeah, that's it. But you can just see by looking at this that if I hold on, let me see. Let's see. Yeah, but so I think I've written something incorrectly in my notes. But anyway, so if I do omega L psi and apply to xi, then I get minus psi squared psi minus, so I get psi squared here, xi minus psi squared. Okay, so I've written something wrong, because I need to get this to be equal to 0. So what should I choose xi to be? I mean, omega to be? Or have I made a sign error somewhere? D star dA. Yeah, that's right. So yeah, so I made I made a mistake here, because I should get that if I act on xi if omega and xi are parallel, then I should get 0 here. But this doesn't look like it's giving me 0. So I must have made some mistake in this calculation. But you get something like this, which should give you 0 if you do this. Maybe this is negative. This could be negative. One of these two might be negative. Okay. So I have so something's wrong here, but we should conclude that this is not elliptic. Okay, so
I've just included something, a stack exchange post that purports to also treat the non-ellipticity via the principal symbol approach. They get the
yeah,
principal symbol is minus zeta squared plus zeta tensor zeta.
Okay, so yeah, so should this, so if that's the case, then this should be a plus, which means I've just written down one of these two incorrectly. One of these two must have a minus in front of them then. Yeah, because in local coordinates, what do you get? So in local coordinates, this is going to look like partial I, A, J. The equation is going to be this minus partial J partial I, A, I. That will be the highest order terms of the Yang-Mills equation. And so here we have Laplacian. And here we have partial J div A minus. And yep. So from this, I think you get psi squared minus and then plus xi tensor psi. Although it's a bit hard to see why this is this, but I think that's the case. Anyway, so the main point is that this equation is not elliptic. But if you just look at this term here, this minus d star a, if it just so happened that d star a was 0, then we'd very luckily have that a satisfies an elliptic equation. Okay, so if we have a solution which also satisfies d star a equals 0, then we have something that satisfies an elliptic equation, and therefore hopefully it will, well, yeah, if we can prove all the corresponding things for these elliptic systems, then we'll have something that has all the nice properties that solutions to elliptic equations have. Okay, so yeah, so I'll write that down. So if we have d star a fa and d star a equals 0, then A satisfies the elliptic equation. A is a solution to an elliptic system. Okay. So so at this point, I was wondering if you could solve I was wondering if you could solve this equation by remove this term, remove this d star dd star term, just ignore it, and then just solve that equation for A. And then if you could use that solution to then do a transform into a solution to the Yang-Mills equation, which has d star A is equal to 0, d star A equals 0. But I wasn't able to, couldn't find that written down anywhere, and I wasn't confident enough to try and write it out here. So, well, we'll now just assume that if we have a solution to the Yang-Mills equation, we want to then transform it into a connection for which d star A is equal to 0. And so we have a solution to an elliptic, A is a solution to an elliptic equation. And then from that, we can hopefully deduce nice analytical properties for A. Okay, so for that, let me just talk a bit about gauge transformations. So just write down a definition. A gauge transformation is a map, capital Phi from P to P, such that it induces, well, which induces the identity on the base and it satisfies this property here. So G phi x equals phi gx. Okay. So basically, we have our principal bundle. Principal bundle has an action of g on it. So a gauge transformation is something that just kind of, if you restrict it onto a fiber, it just kind of is a automorphism of the fibers that is smooth as you go around. Yeah. And also, yeah, and it fixes the fibers as well, right? It doesn't have any kind of, it doesn't do anything to the base space. Okay, so basically you can think of it as, okay, actually, that I think that is a, so I'll write it down here. Well, firstly, the space of all gauge transformations is denoted this P, and it's called the gauge group because clearly it's a group under composition. So one thing that you can think about is that to think about these gauge transformations. So if we have a gauge transformation, is, well, okay, I'll just write, if this phi is in GP, then, so there exists a function sigma phi from P to G such that phi of P is equal to P applied sigma P acting on sigma phi P acting on P. Okay, so it's, so yeah. Okay, so now the thing is that what I want to prove now is that the Young-Mills equations are invariant under gauge transformations. Okay, so we'll have this lemma. This lemma just says the curvature itself is invariant under gauge transformation. So if I have f of the pullback of A under a gauge transformation is equal to the pullback of f under the gauge transformation. Okay, so we can just write that down. That's equal to d phi star A plus phi star A, comma phi star A. Okay, so, well, we know, well, the exterior derivative, we can just pull that out. The pullbacks coming in with exterior derivatives. And if you do some calculations, you can show that this operator, just like how the Lie bracket of vector fields, it commutes with pullbacks. This thing commutes with pullbacks via gauge transformations. And then we get this thing here. Oops. Okay. Okay, so now we can look at the effect of gauge transformations on the Young-Mills functional. So let's calculate Ym of the pullback under gauge transformation of A. That's equal to a by pullback of FA, comma, pullback of FA mu. Okay, so this comes again to some of the kind of stuff I'm less comfortable with all the Lie algebra stuff. But okay, so like I said, if I have a gauge transformation, then I can define a function sigma phi such that phi of p equals p dot p acted on by sigma. So this is a map from p to g sigma phi p. So it turns out with this function, the action of gauge transformations on FA, so I didn't really understand some of this stuff, but the point is the form of this thing, which is that you can add sigma phi inverse applied to F. Okay, and so using this fact, it seems that you can get from this equation, so we get we were able to reduce this because of the add invariance of this killing form, or whatever the spy invariant metric is on the Lie group. So I'm not completely sure about how this works, but if you're extremely uncomfortable with this, then you can look at the version for vector bundles where it's a lot simpler. So yeah, okay, so yeah, so basically we have Yang-Mills functional applied under a pullback. Gauge transformation is just the Yang-Mills functional of A. Right, so if A is a Yang-Mills connection, then so is phi star A. So that's quite useful because if we have a Yang-Mills connection, I'm going to go back. If we have a Yang-Mills connection A that satisfies this equation, then maybe we can apply a gauge transformation to get a Yang-Mills connection that satisfies this thing, which, because it's a gauge transformation, also satisfies this property here. Okay, and then we have a connection that is a solution to an elliptic system. So I'll finish off by stating kind of a theorem which says that this is possible locally provided that your initial connection has sufficiently small curvature. This is due to Coloumb. So yeah, so let's let G be a compact Lie group. And so yeah, so so take some P between n on 2, P less equal to n. Then, so there exists a C greater than 0 and an epsilon greater than 0. So yeah, which which I believe depends on n. I think it only depends on n. Well, n such that so set B to be the unit ball in dimensions. And we can just give it the Euclidean metric. Right? So for any connection A in the trivial principal bundle, with the curvature that has the ln on 2 norm less than epsilon n. So we have the following properties. We have a gauge transformation such that if I write A dash equals phi star A, 1 d star A dash equals 0, 2. 2 is the, if I contraction of A dash with the normal vector to the boundary is 0.
Looks like we've lost our speaker. Maybe we can wait a couple of minutes to see if he makes a comeback.
That must have just been a disconnect, right?
Looks like it.
My camera better now? I don't know what's going
Yeah.
on. Yep, all right, well. Guess we'll just wait.
Oh, I'm on the edge of my seat. I need to know how that theorem finishes.
Yes, indeed. Keep an eye on the old emails.
Yes.
I don't have anything. It's a shame that Paul has teaching at this time.
Well, I guess if this recording works out all right, he and others will be able to catch up later.
Yeah. Yeah, I noticed there's a group of people following on YouTube. It's good.
Does anyone have any Yang Mills related jokes to tell?
Yang Mills is kind of difficult to make a pun out of, right?
Probably.
No frills, Yang Mills, not sure. Hmm.
Oh, well, we'll give it a couple more minutes and then we might have to call it.
Yeah, I reckon give it 2 more minutes. Maybe his equipment's broken.
Oh, I was lucky we got this far.
Almost to the end, honestly.
Yeah.
I mean, Vishnu's the next speaker as well anyway, isn't that right?
Yeah, he was hoping to do another session.
So he can just pick up where he left off.
Yes.
It's totally fine.
Even Google doesn't help very much when you search for young Mills jokes. I feel like there's an empty market here.
Yes,
Oh,
let's publish a pamphlet.
that can be homework for everyone then.
Hmm.
This has never happened before, I think.
Yeah, it's
in
kind
our
of
seminar.
incredible in 5, what are we up to? 5 seasons of
Yeah, I think so.
seminar? This is the first time our speakers actually dropped out. I mean, like, unintentionally. Intentional dropouts happen all the time.
Yeah, perhaps one problem with online seminars, you can't block the door and stop your speaker from running away if it all goes wrong.
Yeah, you chain them down until they finish their seminar. Yeah.
All right, let's call it then.
Yep, I think now. Oh, he's back.
Oh,
The 2 minutes was accurate.
Oh,
When did my Zoom crash?
A good number of minutes ago.
Oh no, because I
Just before
kept
you're about
talking.
halfway through the
oh
theorem.
no. Yeah. Well, maybe you can show us show us
Oh
what
no,
you've written.
that's unfortunate because I just continued, and at the end no one said anything, and I was like, what's going on? Okay, so okay, in 8 minutes, I will do everything I did. Where did I disappear?
You were in the middle of stating your theorem.
Oh, okay, that's
The-
good. That's good. I thought I was like maybe all the way down here or something. Okay, here, right?
Yeah, so I think you were in the middle of number 2, I think.
Okay, great. That's good. That's good. Okay, that's better than I expected. Anyway, so okay, so yep. So okay, so yeah, so okay. Firstly, we have it satisfies this divergence free property, which is the kind of the main property we want. On the boundary of the ball, this connection contract with the normal vector to the boundary of the ball gives me 0, and also we have control over a dash in W in LP, but we also have control over its derivative in LP by the curvature, by the p norm of the curvature, which is better than expected, especially for the original thing where we probably would only expect to get just control over A under curvature. So the main things that I said at the end were just that this is not the original. This is usually not how you see the theorem. Usually you would see it for vector bundles, especially in the original paper and stuff. And this, I believe that this ball, the metric doesn't have to be the Euclidean metric. It is just some metric that is some prescribed distance away from the Euclidean metric. So instead of it being there exists C and epsilon, there'll be C epsilon delta, where the metric on B is a delta away. And also Uhlenbeck's original theorem actually proves all of this for connections that are only in LP. So I think that's, I don't know how to prove that, but that's I think much more general. And yeah, and then yeah, so what I'll do next week is I'll prove this or a much simpler version or a simplified version of this. There are some questions that I might look at. What is a moral fiber? Principal bundle with a moral fiber. Okay, I think I'll stop there.
Cool. Let's thank our speaker. Does anyone have any questions for Vishnu about his content from this lecture?
Thanks, Vishnu. Thanks for the talk.
Nice.
I have a couple of questions. Would you mind sharing your screen again?
Yep.
I think maybe the answer to this question is I need to remember the notation, but you're assuming that A is a Yang-Mills connection from the get-go in this theorem?
No, this doesn't have anything to do. It doesn't require any kind of assumption on A, except for that it has curvature bounded like this. That's it.
Oh, I see. So you're not Oh, I see. So A dash does not actually satisfy the Yang-Mills. That's not what the first condition says.
No, it's just saying that there exists a gauge transformation for which all of these properties are satisfied.
Okay, so I see. Oh, okay. So the fact that D star A dash equals 0, that's what you're eventually going to use to get rid of that D star that you don't want in your equation, I presume.
Yeah, I'm not sure if the purpose of that is to solve the Young-Mills equation. So I think the purpose of that is to just prove other kinds of analytical results.
Oh, okay.
I tried to find a way, because if you assume you can solve elliptic systems, then can you solve the Young-Mills equations? I think that's true based on, well, firstly, my thought was maybe you can solve this equation, like you just take this, well, sorry, no, that equation. You take this equation, you just remove this part of it, and then you solve that equation. And then you apply a gauge transformation for which A is now has D star A equals 0.
Yeah.
And then
that's elliptic-ish.
Well, the problem is that I wasn't 100% convinced that pullbacks under gauge transformations commuted with the exterior, the adjoint of the exterior
Oh,
code.
D star.
Right, because
it sounds like it should be true.
yeah, it sounds like it should, right? But in general, you can't commute with the co-differential with a general pullback. You have to have an isometry. But so a gauge transformation, well, it probably does. The reason being that if you look at the Yang-Mills, like if you look at the Yang-Mills function, I'll just use this form of it. If I have a gauge transformation here and the exterior covariant derivative, maybe I can move that gauge transformation across using add invariance and then move the exterior covariant derivative across and then move it back or do something else to get to commute those two things, something like that.
Okay.
Yeah. But if that's the case, if gauge transformations commute with this, then certainly you can do that process to solve the Yang-Mills equations.
Cool. I did have one more question about the Uhlenbeck theorem. It doesn't seem particularly satisfying to me that you have to assume small curvature, because I assume that integral that's a scale invariant condition, right?
Yeah.
So you can't just you can't just fix the problem by scaling away. Are there counterexamples to this theorem when you don't have such small curvature?
I have no idea, but well, if we look at the statement of Uhlenbeck compactness, does that require anything? Like, does that have requirements on the curvature of each of the elements in the sequence? If it does, then clearly this is then maybe.
You can ask a question.
Yeah, I'm not sure.
Cool. Any further questions?
Sorry, Valentina's just talking to me. I was just gonna comment that it's not like a global small curvature. It's like B's like a ball, so you can think of it as like a local smallness, I think.
Oh, really?
Isn't that right?
But typically, isn't M usually assumed to be compact? So doesn't it not matter?
I mean, B doesn't have to take up the whole space.
But like if you were doing this globally on a principal bundle, isn't the whole principal bundle compact usually? Like the base space is also compact. So if you had small curvature, so doesn't this also require small curvature everywhere?
Maybe. I'm
Well,
just
this is just the local
observing from
result,
the
though, so it
hypothesis,
doesn't.
that's all.
Glenn, are you saying that you can play games to always make curvature small and get the same result?
No, I'm just thinking in terms of concentration compactness theory. So we often prove that, you know, you have this it is a scale invariant condition, but it's on a small ball,
Mm.
and you can, if you have, so for example, a smooth immersion, then you can always find such a ball on which to do your regularity. And I mean, the radius, you might be able to add up all the balls over the whole manifold if it's compact, but
So I see
the
you're
number of
saying
balls
that
that you need is like dependent on how, like, the geometry of the manifold. So when you have an time, everything depends on time. You're not sort of making any claim about how many balls you need. You're just saying what happens on this specific ball.
So yeah, so is one part of that argument one part of that argument to say that first you just choose an initial ball that's small enough for which that curvature is small, and then just turn it into the
Yeah,
unit
it's
ball?
related to the scale invariance. So if you imagine like inflating your manifold, then because the integrand is scale invariant, then it's just the domain that changes. And so you can always, as long as it's bounded, like as long as it's regular, you can always scale to get, this hypothesis in a ball.
So maybe it is just an
Okay.
artificial hypothesis to make the statement of the
No,
theorem
I
cleaner?
think it's just like a standard hypothesis for
Yeah.
concentration compactness.
Yeah, cool.
I'm sorry, my camera's doing that thing again. Oh, it's annoying the heck out of me.
All right, cool. Let's leave it there. Let's thank Vishnu again for a lovely talk. All right, thanks everyone. I'll
See you
stop
next time.
recording now.
Cheers, Tim.